there. We have 2 sections left. They're kind of little sections. So, yeah, there we go. I got a yay for trig. I did cover 3.3 and 3.4 on Monday, but just a little bit out of order, right? And then we have 3.5 and 3.6, which are kind of, there's not a ton of questions in there. So that helps us out, right? And we're going to do some of the questions here while we talk here today in class. So basically, 3.5 is using exponential and logarithmic models, and 3.6 is nonlinear models. So they're kind of the same thing. Basically, we're going to be talking about how do we use these exponential functions that we've been learning about to model different information. So the first thing that I want to do, which I have pre-set up on Desmos, is talk about, let me leave this up in case we need the chat. Talk about these, if you have your notes, at the top of 3.5, it says the 5 most common types of mathematical models involving exponential functions and logarithmic functions are as followed. So these are basically 5 of the most common exponential and logarithmic models. The first 2 are the most common by far. And then the other 3 are common, but not quite as common. So the first 2 are exponential growth and exponential decay. All right. So we want to kind of have it in our mind what we think that looks like. So down here we have graph A, B, C, D, E, and F. They're kind of over 2 pages. But in your mind, if I said exponential growth, what would you think of? Which letter? Which one looks like exponential growth? Just kind of feel it, just based off of the words alone. Oops, I didn't mean to do that. Sorry. C, right? C looks like exponential growth, right? It's just like starting off and then it grows like crazy at the end. Okay. And so then if that's exponential growth, which one looks like exponential decay? Decay looks like this, right? It's like, it's dropping off. That's decay. So hopefully, oh, there you go. I saw it, Greta. E. All right. So yes, E is decay. See, this one is growth. This is decay. So hopefully, if someone said to you exponential growth or exponential decay, in your mind, you should have some kind of a guess as to what that looks like. Okay. I'm going to skip over 3 and 4. We'll come back to those. The last 5, the 5th most common type, is logarithmic models. Okay. Now think about this. We talked about exponential growth and decay, right? And we talked about how logarithm is the inverse of exponential growth. So if this is exponential growth, what would an inverse look like? Which A, B, D, or F, which one do you think would be the inverse of exponential growth? D, right? D looks like that because if you kind of think about what does exponential or what the inverse looks like, the inverse is usually when we reflect about y equals x. And we kind of talked about that back in the beginning. So this would be a logarithmic function. I could just tell you based off of that. B also is a logarithmic function. It's just kind of had some crazy things done to it. Okay. And then the last 2 in the middle, or 3 and 4, are the Gaussian and the logistic growth model. So we haven't talked about those, but I have those already pre-typed into Desmos, so you don't have to wait for me to do it. So let's make Desmos a little bigger here. Okay. So let's change our numbers here to something. Okay. So if I turn on exponential growth, right, exponential growth looks something like this. You can change it based off of your numbers, right? Here, I'll make my number there. Here's an exponential growth curve. Y equals A to the E to the a times e to the bx power, exponential growth, and here's exponential decay, drops off. Okay, and then if I throw on there my, this is a natural log function, but if I throw my natural log function on there, right, you can see that it's like the inverse of your exponential growth. Okay, so those are those three. Now we have these other two, which are the Gaussian model. So the Gaussian model is actually kind of cool. It has this formula here, A times E, and then E is raised to kind of a crazy power, X minus some constant B squared divided by C. So the Gaussian model actually looks like this. It's like a little blip. And if we change our numbers around, can we, yeah, we can move this back and forth. We can make the amplitude of that bigger. Oops, we can flip it upside down. All right, so has anyone seen anything that looks like this before? Looks like a what? Looks like a hill, right? Oh, wait. It looks like a hill. I just want to make sure, did I hit? Okay, I did hit start recording. I thought I forgot to do that. Sorry, guys. Does this look familiar, this Gaussian model at all to anybody? Besides looking like a hill. So the Gaussian model is actually what a lot of standardized tests and bell curves are modeled after, or if you're trying to like normalize data. So what I mean by that is like if you're trying to take the ACT, hopefully you don't get a 2. If you're trying to take the ACT, right? Most people are going to get, I don't know what the average score is. I did a total take a guess. I don't know, 22. So say most people get a 22, right? On the high side, the highest you can get is 36, and the lowest you can get is 0, right? So when they get a bunch of people to take the ACT, the chart should look something like this, where most people should get somewhere in this middle, right? And then the higher score you get, the less people get that, and the lower score you get, the less people get it. So that's a Gaussian model. It's actually an exponential model, and it's another way people call it is a bell curve. So I think those are kind of interesting. And that's what it looks like. And it's a form of an exponential equation. Okay. And then the last one, equation number 4, is a logistic growth model. So here's logistic growth. This kind of looks like a combination. This reminds me, logistic growth reminds me basically of a combination of exponential growth, and if you would combine exponential growth and then kind of flatten it off, right? So you start off, then you grow, and then you flatten back out again. So this is logistic growth. Okay, so then if I flip back to my notes for homework 1 through 6, if I wanted to match these up, A would be a Gaussian model, right? It's your bell curve. B and D would be logarithmic models. E or C would be exponential growth, and E would be decay, and this would be a logistic growth model. Okay, so you can kind of look in here and figure out based off of you can either type them in and kind of see what they look like, or based off of the equations. Just note that the exponential growth has a positive exponent, and the exponential decay has a negative exponent, right? So having the negative up there, the exponent means decay. Okay, I'm going to come back to the second part of 3.5, but while we're here, let's look at 3.6 and number 1 through 8. It says, determine whether the scatter plot could be best modeled by a linear model. So linear means line, right? A quadratic model, so that's a parabola. an exponential model. So we just talked about that, right? A logarithmic model or a logistic model. Okay, so let's kind of do these together. What does number one look like to you? Well, no, let's skip that. What does number two look like to you? How would you best model this data? Linear, quadratic, exponential, logarithmic, or logistic?
Linear.
Linear, right? That's totally aligned. All right, four. Let's look at four. So this one's a little bit more tricky, right? Not linear, right? Do you think that's better modeled by a quadratic or an exponential model?
Exponential.
Yeah, that's exponential, right? Versus number three, which is quadratic, right? So this is probably better modeled by exponential. Now, number six has this funny, like, we're flat, then we grow, then we're flat. So this is the new one we learned. So what kind is this? You can look it back. This is the logistic, right? Model. And then number eight, we're back to a linear model. Okay. Um, does that make sense to everybody? Well, Greta and Connor.
Yep.
All right, cool. Um, okay. So now we're talking about modeling and graphing and all that good stuff. We're going to stay in 3.6 and then I promise we'll go back to 3.5. I won't forget about it. Um, so this 1 through 8, we basically did 2 through 8. We basically did your homework for that. And then you have problems 9, 11, 15, 19, and 23. So what this is going to be is in 9 and 11, 9 and 11, it says, well, in 9 through 14, use a graphing utility to create a scatter plot of the data. Decide whether the data could best be modeled by a linear model, an exponential model, or a logarithmic model. Okay, so for example, if I do number 12 that's on here, okay, what this would look like is you're going to use your data points, right? I got to get rid of all my pretty graphs. And you're basically going to add all your data points in by adding a table, right? So you're basically doing what you did in 1 through 8, but you have to put the points in yourself. Again, if you're using your TI, you can do this if you go to sorry, I'm having a moment. I'm looking at my calculator here. You want to insert the table, but I'm trying to remember what button it's under. There is a table button, but I think all right, let me look that up. There is a way to put it in under your TI. If you're trying to do this after you listen to the call, just Google how to input a table into your TI, and it should tell you. Okay. So basically all I'm doing is writing these data points in, right? Very exciting. Can you see how well my typing skills are? Right? 8 and 1.4. Oops. Not very good, apparently. Okay, so I typed my data points in. I have 1, 2, 3, 4, 5, 6 data points. 1, 2, 3, 4, 5, 6 data points. And I zoom out and, okay, based off of my data points, how do you think this is best going to be modeled? My choices are linear, exponential, or logarithmic. None of the above. No. What do you think, Connor?
Exponential.
Exponential. I agree with you, Connor. It's going to be exponential, right? It's not going to be exponential growth. It's going to be exponential decay, but it's going to be exponential because it's got that curve in there. It's not linear. Logarithmic would look something more like this, where it starts off and flattens out. Okay. So that's all you have to do for that. So for 9 and 11, you're just going to see what kind of model you need. Okay. And then in 15, basically in 15, 19, and 23, you're going to use the regression feature of your calculator to find what the regression would be. Okay. And instead of you watching me type in the data, I'm just going to show you how you would use it. So for example, in number 15, it says, use the regression feature of a graphing utility to find the exponential model y equals a b to the x power for the data and identify the coefficient of determination, which basically means your r squared value. And then model in the same viewing window. And then in number 19, it wants you to regress using a logarithmic function. And in 23, it wants you to regress using a power model. Okay, so I'll do that for this data so you can just see what this looks like. Oops, that's not what I want to do. I want to do this. So for this set of data, when I want to regress it, remember you're going to use this kind of weird nomenclature. So it actually tells you at number 15, you want the exponential model, which is y equals a b to the x power. Okay, but this isn't how you exactly type regression in, right? Instead of an equal sign for regression, you have to use the tilde. Okay. And then we have to tell which x's and y's we want. Well, we want x sub 1 and y sub 1. We want to pull from that data. So this needs to be from x sub 1. And the y needs to be pulled from y sub 1. Okay. So now that I did that, it shows me the regression, right? So in order to model this data, which actually it models it perfectly, perfect exponential model, right? It tells me that my A value is 14.86, right? 85. And my B value is 7.743043. Okay. And then the last thing it asks for is the coefficient of determination. So the coefficient of determination is actually this r squared value. I don't know if you remember back from algebra 2, but the better your r or r squared value is, the closer to 1 it is, the better your regression is. So this is pretty much a perfect regression, right? The only thing better would be 1 if we could model it perfectly, but this is pretty much a perfect regression. Okay. So then, for example, that would be how I would do something like 15, right? If I wanted to model this data using a logarithmic model, I have no idea how this logarithmic model is going to work, but I'm going to do the same thing, but I'm going to use the expression for the logarithmic model. So instead, it's going to be a. It's probably not going to model it very well, right? Because it's not a logarithmic. B. So I'm trying to model like something like in problems number 19 through 22, but it's probably not going to work very well because this is not the right model for my data, right? But I still just want to show you that if you type it in, you can get a model for it. It just might not be a good model. Okay. Oh, well, it came up with a decent model for me. So if you use this, sorry, if you use the regression model for the logarithmic model, which again, if you look at your notes in 19 through 22, it says the form y equals a plus b times the natural log of x. And I model it. We actually get a pretty decent regression for those data points, right? So you get a coefficient of determination of 99.66, and then you see that what your A and B would have to be to get that. So this is your purple curve, okay? The green curve looks like it models it a little better. So again, we can kind of force things to do things, but that's that. Okay, do you guys think you could tackle 3.6?
Yep.
Cool. Greta, you think you got it? Probably. You can do it. We're just putting some data points in there and regressing them. You can totally do it. Okay. Last part. Back to 3.5. So, the last few problems have to do with compounding interest. Okay? So, we should remember what the formula for compound interest is. Will be the first important thing, right? So back from, I think it's in 3.2. You go flip back. No, I think it was the first section, 3.1. Okay. So if you go back to your notes on 3.1, or I'll write it up on there, we learn that if you have continuously compounding interest, the formula is A equals P E R T. It equals PERT. Okay, so A stands for the amount that you have after some time, right? Amount, after time, if you can even read that. Okay, P is the principal or the initial amount. Okay, R is the rate. And what do we always put rate in? Do we put it in percent or do we put it in a decimal? Percents just look pretty, right? The rates always have to be in a decimal. All right. And T is time in years. Okay. So we have 7 through 15 odd. So we're going to do some of these. It says compound interest. Okay, so in exercise 7 through 14, we're going to be dealing with this idea of compound interest and our savings accounts and see how they do. Okay, so complete these tables for a savings account in which interest is compounded continuously. Okay, so we have our initial investment, right? And we have our annual rate, and we want to know how much time it would take to double our account. Okay, so let's figure out this guy first. So what you're going to do is you're going to use this formula every single time. It's just going to be variations of this formula, right? The initial investment is the principal. So that's $2,000, right? Times E. And then the rate is 1.5%. So we write that as a decimal, right? 0.015. And we want to know how much time it takes to double. Okay. So we're trying to find T, time. Okay. And what does it mean if we double our initial amount? How much money do we have if we double it? We have $4,000, right? Is double 2,000? Last I checked. Okay. Excuse me. So how would you solve this kind of equation? That's the question. That's what we need to know, right? So we need to get t by itself, but t is in it's an exponent. T is an exponent. So we need to do some work to kind of get t by itself, right? The first thing that I want to do is I want to divide both sides by 2,000. So I end up with 2 equals e to the 0.015 t power. Okay. So this is where all of these like rules and things we learned about exponents and logarithms and rules and everything, this is where it comes into play. So back in 3.3, which I forgot to teach you, back in 3.3, we learned about something called the power property, which means that if you take like well, we learned if you take like the natural log of e, right? We can do that to both sides, and that's actually going to take our exponent and bring it down to the front. Okay, so what do I mean by that? What I mean is that I can actually, when I have this, I'm allowed, just like I can multiply both sides of the equation by a number, divide both sides of the equation by a number, I can actually take the natural log of both sides of my equation. You're allowed to do that. Okay, and when I have a natural log of e to some exponent, that just simplifies to 0.015 t. The exponent gets to come down to the front, and the natural log of e is just 1. So that's actually why learning all those rules is important, because it lets us do this. So now that we have the natural log of 2 equals 0.015t, the last thing I have to do is divide both sides by 0.015. And I use my calculator to find that t equals, if I plug it in, I get 46.2. So it takes 46.2 years for my initial investment to double if I have an investment rate of 1.5%. 46.2. Okay. Another way that you could look at this, honestly, or you can double check your work, or if you're taking a standardized test and you need to go really fast, okay, is if I go back to my original, right? I want to know when I have $2,000, right, times e to some, my rate is 0.015 times x. Okay, I want to find out when that reaches $4,000. I'm basically graphing both sides of my equation. I'm going to need to zoom way out, right? Because my initial amount is $2,000. So I need to find out, I need to set my window better is what I need to do. My x-axis needs to go between like 0 and 100 years. And my y-axis can go between like, yeah, we'll do 0 and 5,000. Okay, so this is how your money grows, right? Throughout the years. And you can see that when X number of years, which is 46.2 years, when I have 46.2 years, I get $4,000. Right? So that also means if I'm at 20 years, I have about, I'll get my cursor close, I have about $27,000, right? If I leave it in for, let's see, 40 years, I have 36,400. $3,600. I can't even talk. $3,644. Okay. So that's kind of the model of your exponential growth of your compounding interest and how you would do that. So the next part of my graph is, what is my amount after 10 years? Okay. If I have my graph up, my amount after 10 years is what? I just, after 10 years, I should have $2,323 and 60 something cents. Oh, I moved my cursor. Okay. If I did that algebraically, if I wanted to know how much money I have after 10 years, this one's actually pretty easy, right? It's A equals PRT. So my principal is $2,000. E times my rate, which is 0.015, times my time, which is 10 years. So you just plug that into your calculator, plug it in, and you get $2,323.67. Okay. So then all the rest of these problems are going to be variations on that. They're all going to be, one of these variables is going to be missing. So here we have the annual rate is missing. We have to find the R. This one we have the initial investment is missing. So we got to figure that out. So we have different variations of that. Give me 1 second and I'll be right back. Hold on a second. Okay, thank you. All right, so what do you think? Do you want to see one more example? Let me do one more example algebraically of how we would do it.
I think I got it.
You got it? All right. What about you, Greta? You want one more algebraic one, or you think you got it? The weird part is the how you can take the natural log thing. You think it's good? All right. Cool. I'm good with that. I can always do another one on Monday in class. Yeah, just remember if you have like, well, let me just tell you. So like if you have number 10 and you're trying to find the rate, right? P equals, or yeah, A equals P-E-R-T, right? A equals P-E-R-T. So in number 10, you're trying to find, why does it not want me to write a line that way? Doesn't like it when I write a line up and down for some reason. Okay. So like number 10, if you're trying to find the annual rate, if you know you invested $10,000, okay, and it takes 12 years to double means to make to $2,000. That means you know that the time is 12 and the rate is R. Okay, so that's how you would set up to find the annual rate. You're going to divide both sides by 1,000, right? And you get 2 equals E12 to the R power. Okay, in order to get that rate down to solve it, what you want to do is you want to take the natural log of 2 on one side, and you want to take the natural log of E to the 12R power. That 12R gets to come out front because it's in the exponent, and the natural log of E is just 1. So it's a really powerful way to solve it. Okay. Cool. All right. And then there's one word problem on there. There is one word problem, and Let's see here. I'm finding it. 3.5, number 29. So I'm just going to go ahead and do this word problem. Let's just do this word problem together. So Greta and Connor, you guys can help me, and then you can be done with your word problem. It says the population, so this is number 29 on 234. Can't say numbers today. The population P in thousands of Reno, Nevada can be modeled by the population in thousands is P equals 134 e to the k t power. This is the population of Reno, Nevada. T is the time in years. Okay. And when T equals 0, that corresponds to 1990. Okay. And then it says in 2000, in the year 2000, the population was 180,000 people. That's a data point that we have. In the year 2000, the population was 180,000 people. The source is the U.S. Census Bureau. Find the value of K for the model, round your result to 4 decimal places, and then use your model to predict the population in 2010. Okay? So the one thing to note is that population P is in thousands. Oh. Okay. All right, so let's kind of plug in what we know. Okay, so we know that, well, yeah. We know that in 2010, or 2000, in year 2000, there were 180,000 people in Reno, Nevada. So what will we put in for P? If we want to use this data point, then in 2000, the population was 180,000 people, what will we put in for P? We would actually put in just 180 because they tell you that P is in thousands. Does that make sense? Okay. And then we know it's modeled by 134 e to the k t power. So now what do we put in for the time t? Well, time is 0 in 1990. So what would time equal in 2000?
10.
10, right? So now we have to find k based off of this information. So what should we do? Same thing we were just doing with compound interest, right? We're going to divide both sides by 134. And I don't even know what the numbers off the top of my head are, so I'm going to do that here. Da, 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 da. 180 divided by 134 is 1.343. And I might even leave that as a fraction. Equals e to the k 10k power. So now what do we have to do to get k down below? What should we do?
Take the natural log.
Yep, take the natural log of both sides, right? I'm going to leave this as a fraction so we can be more accurate. I know I put it as a decimal, but I'm going to leave it as a fraction. Take the natural log of both sides, right? 10k. And so what this side is going to become is just 10k equals the natural log of 180 over 134. or divide both sides by 10. I know I'm being a little bit sloppy here, but you guys get the idea. So all of that to say that if we figure out what K is, I gotta get out. You gotta get a better calculator. Desmos, where you at, guy? Desmos. So we're gonna take the natural log of 180 divided by 134. And we're going to divide that whole thing by 10. And we end up with a K value of 0.0295. And they told us to round it to the nearest, 4 decimal places. There we go. 0.0295. So then the second part was, if you wanted to predict the population in 2010, let me kind of wrap this all up, right? So now our model up here, instead of a K up there, it's going to say, right, it's going to say 0, I need to write 0.0295 T, right? And then I need to write a line here so you know. That's by itself. So if I want to find the population in 2010, what am I going to put in for T?
20.
Yep, exactly. That's it. That's all you're going to do. So now you have not so much homework left. So that wraps up chapter 3. So that means the homework and the test will be due not on Monday, the 4th. It'll be the 11th, I think it is. So I will go ahead and send that out so you guys can work on it. And thanks for coming today. Let me know if you have any questions, and we'll start with some exciting trigonometry on Monday. All right, bye guys. See you on Monday. Thanks for coming.
Thank you.